Elementary number theory is the foundation of all number-theoretic inquiry. It studies the arithmetic of whole numbers and the essential properties such as divisibility, primality, greatest common divisors, and modular arithmetic. It underpins more advanced disciplines and is applied in everything from cryptographic systems to computational algorithms. In its simplest form, elementary number theory begins with questions about divisibility and the nature of prime numbers, extending to concepts like the greatest common divisor and the principles of clock arithmetic or modular congruence. To these are added fundamental algorithms such as Euclid's method and theoretical results concerning the infinite nature of primes. These concepts form the hierarchy that underpins analytic and algebraic number theory. The fundamental ideas can be formally described as divisibility relations, prime factorization, greatest common divisors, modular arithmetic equivalence classes, the Chinese remainder theorem, and Fermat's Little theorem. This field requires no advanced machinery, only clever reasoning about integers. Analytic number theory uses continuous mathematical tools to study discrete number-theoretic objects, enabling the analysis of prime distribution and the behavior of arithmetic functions. Unlike elementary number theory, it is not limited to direct integer manipulation. Instead, it introduces functions from calculus such as limits, integrals, and complex analysis, which can assume different values depending on the analytical context. Its foundations include the transformation of number problems into continuous functions, the study of convergent infinite series and products, the application of complex analysis to counting problems, asymptotic analysis of arithmetic functions, and the investigation of special functions like Riemann zeta function. It also covers the statistical distribution of primes, L functions of various types, analytic continuation techniques, and estimates for arithmetic sums. At more advanced levels, analytic number theory studies the zeros of zeta and L functions, exponential sums, sieve methods, circle methods, the Riemann hypothesis, and the intricate connection between function theory and prime number distribution. This field expands the scope towards results such as the prime number theorem, which are fundamental in understanding the asymptotic density of primes, probabilistic number theory, and modern cryptanalysis. Algebraic number theory studies number systems beyond the integers, their properties, and the relationships between algebraic integers, ideals, and number fields spanning from quadratic fields to general number fields, and in advanced applications, fields of arbitrarily high degree. Its foundations began with the observation that unique factorization fails in certain rings, leading to the introduction of ideals as a restoration of factorial structure, the study of number fields as extensions of the rationals, and the analysis of how rational primes split or remain inert in these extensions, from which concepts like algebraic integers, class groups, unit groups, and Galois groups are constructed. It includes branches such as class field theory focused on abelian extensions and local global principles which describe how solutions and completions determine global solutions. Algebraic number theory combines the structure of rings and fields with Galois theoretic techniques to solve Diophantine problems covering everything from the study of unique factorization domains, Dedekind domains, and splitting of primes to ramification theory, discriminants, different ideals, and the intricate behavior of field extensions. Transcendental number theory studies the distinction between algebraic and transcendental numbers as well as their classification and the methods for proving transcendence. Its foundation lies in the fundamental dichotomy that algebraic numbers are roots of polynomial equations with integer coefficients while transcendental numbers are not, which establishes a profound separation in the number continuum. For example, the square root of 2 is algebraic as it satisfies the equation x squared equals 2, whereas pi and e are transcendental. In addition to classifying individual numbers, it addresses the algebraic independence of sets of numbers through criteria such as the Lindemann-Weierstrass theorem and Scanuel's conjecture. It includes techniques for proving transcendence such as auxiliary function methods, Baker's theory of linear forms and logarithms, and measure-theoretic approaches, as well as the study of periods, exponential functions, and special values of analytic functions. Its scope extends to questions about the transcendence of constants arising in analysis, such as values of the Riemann zeta function at integers, essential in understanding the deep structure of mathematical constants. Thanks to the rarity of provable transcendence results, transcendental number theory reveals that most real numbers are fundamentally unreachable by polynomial algebra, arithmetic geometry, synthesized through the work of Grothendieck, Weil, and Deligne in the 20th century, is based on earlier ideas from Diophantine, Fermat, and Poincare. Arithmetic geometry studies the intersection of number theory and algebraic geometry, connecting Diophantine equations with geometric structures. It is structured into two fundamental perspectives: the geometric viewpoint, which analyzes solution sets as varieties with topological and algebraic structure, and the arithmetic viewpoint, which studies rational and integral points on these varieties. Added to these is the cohomological perspective, which extends the concepts to the study of E-tail cohomology, Galois representations, and sheaf-theoretic tools, incorporating structures such as schemes, morphisms, fibers over primes, the wheel conjectures, and the analysis of elliptic curves, abelian varieties, and higher dimensional varieties, all essential in modern cryptography, coding theory, and pure mathematics. It precisely introduces the notion of a scheme, a cornerstone for defining smoothness, properness, and separatedness, and extends the study to the behavior of varieties over different fields and rings such as finite fields, p-adic fields, and function fields. For example, if a variety V is defined over the rationals, studying its points of bounded height reveals distribution patterns analogous to analytic density. This field includes topics such as moduli spaces, the Birch and Swinnerton-Dyer conjecture, Falting's proof of the Mordell conjecture, Diophantine approximation, Manin's conjecture, rational points on curves of various genera, reduction theory, and the arithmetic of function fields. Its applications range from proving Fermat's last theorem and designing elliptic curve cryptography, even in everyday applications such as secure internet transactions, digital signatures, and blockchain verification. Arithmetic geometry turns abstract algebraic structures into practical cryptographic protocols. Diophantine geometry consists of mathematical frameworks that describe how the solution sets of polynomial equations behave with respect to their arithmetic and geometric properties, allowing for the classification of equations by the finiteness or infiniteness of their integral and rational solutions. Instead of establishing direct numerical solutions, these frameworks express relationships between the geometry of varieties and the distribution of rational points, focusing on the qualitative structure of solution sets. They are classified into curves with genus 0, 1, or greater than 1, and higher dimensional varieties with varying Kodaira dimensions, each exhibiting distinct solution behaviors. Among Diophantine equations, curves of genus 0 typically have infinitely many rational points if any exist. Genus 1 curves or elliptic curves possess a finite basis for their rational points by the Mordell-Weil theorem, and curves of higher genus contain only finitely many rational points by Falting's theorem. A foundational example is Fermat's equation x to the n plus y to the n equals z to the n, whose only integer solutions for n greater than or equal to 3 are trivial, as proven by Andrew Wiles using elliptic curves and modular forms. This describes the rigidity of higher-degree Diophantine equations, applicable in understanding algebraic curves, rational approximation, and the limitations of polynomial solvability. Higher dimensional cases include the study of surfaces, threefolds, and their rational and integral points, governed by conjectures such as the Bombieri-Lang conjecture, Lang's conjecture on varieties of general type, and the Batarev-Manin conjecture concerning points of bounded height. P-adic number theory is the structural language of local analysis in number theory, as it describes and organizes number systems based on divisibility by a fixed prime. A p-adic number is constructed through completion with respect to the p-adic absolute value, where closeness is determined by divisibility by high powers of p rather than Euclidean distance. For example, in the 5-adic numbers, 125 and 130 are extremely close because their difference is 5, divisible by 5 to a high power. The basic structures include p-adic integers, the field of p-adic numbers, p-adic expansions analogous to decimal expansions but in base p, the p-adic absolute value which reverses the usual size intuition, and Hensel's lemma which allows lifting solutions from modular equations to p-adic solution. At more advanced levels, p-adic number theory addresses p-adic L functions and their interpolation properties, which allow the encoding of arithmetic information into analytic objects, as well as p-adic Hodge theory, crystalline cohomology, and the role of Fontaine's period rings in connecting p-adic representations with geometric objects. Modular Forms theory studies functions on the upper half plane that exhibit extraordinary symmetry under the action of discrete subgroups of the modular group and encode deep arithmetic data through their Fourier coefficients. These functions satisfy specific transformation laws under linear fractional transformations and possess holomorphic or meromorphic behavior with controlled growth at cusps. Thus, a modular form of weight k for the full modular group transforms in a prescribed way under the action of SL2Z, whereas forms for congruent subgroups exhibit refined symmetry adapted to specific modular curves. From this arise notions such as cusp forms, Eisenstein series, Hecke operators which act on spaces of modular forms and reveal multiplicative structure, new forms which are eigenforms for all Hecke operators, and the connection between modular forms and elliptic curves through the modularity theorem. It also addresses L functions associated to modular forms, the Ramanujan-Peterson conjecture, congruences between modular forms, and the Eichler-Shimura isomorphism linking modular forms to cohomology. Automorphic forms theory studies functions on higher rank groups and symmetric spaces that generalize modular forms to settings of greater algebraic and geometric complexity. Unlike modular forms, which are restricted to GL2 in the upper half plane, automorphic forms are defined on quotients of semi-simple Lie groups by discrete subgroups and on adelic groups. Its foundations include representation theoretic perspectives, where automorphic forms correspond to vectors in infinite-dimensional representations, the study of cuspidal and non-cuspidal spectra, and the role of automorphic L functions in encoding arithmetic and analytic data. Automorphic forms theory also encompasses functoriality conjectures, which predict relationships between automorphic representations on different groups. The trace formula of Arthur and Selberg, which provides a powerful tool for counting and analyzing representations. This field is central to the Langlands Program, the vast web of conjectures connecting number theory, representation theory, harmonic analysis, and algebraic geometry. It seeks to classify all automorphic representations, understand their L functions, and establish deep reciprocity laws that unify disparate areas of mathematics through a universal arithmetic geometric dictionary. Iwasawa theory studies the arithmetic of infinite towers of number fields and the behavior of arithmetic invariants as one ascends these extensions. Unlike classical algebraic number, it deals with objects that evolve through infinitely many layers indexed by p-adic analytic structures. Its foundations lie in the study of ZP extensions, infinite Galois extensions whose Galois groups are isomorphic to the additive group of p-adic integers. The analytic part constructs p-adic L functions that interpolate special values of complex L functions, while the algebraic part studies modules over the Iwasawa algebra and their structure. Iwasawa theory is fundamental for understanding the deepest asymptotic phenomena in arithmetic, revealing hidden growth patterns and providing a bridge between p-adic analysis and classical number theory.